Welcome to this episode of Real Chemistry. I'm Dr. Morris. Today we're going to be talking about weak acid, strong base titrations. Specifically in this case, we're going to be dealing with the weak acid HF, which is going to start down in our flask, and our titrant, the thing we're adding, is up here, and it's NaOH. When we add those together, here's a bigger picture of my flask. What happens is down here we have our HF, right? Some of those are together and some of those are separate because it is a weak acid. And when I add a sodium hydroxide, that gives me sodium plus and OH minus. The OH minus and the H plus are going to react to give me just plain old water. And so what happens then is as we add our strong base, we're dropping the concentration of H plus and slowly increasing our pH. Our goal in this video is going to be to track that pH as the reaction runs. Notice if we add just the right amount of sodium hydroxide so that it's equal to the HF, then we'll have only water left. All of our HF will be gone. That's called the equivalence point, when the acid and base are exactly equal to each other. We're going to do two pH calculations in this video, one before the equivalence point, when we haven't added enough sodium hydroxide to equal the acid, and one after the equivalence point, when we've added more than enough sodium hydroxide to equal the acid. The only calculation we won't do is the pH at the equivalence point. That will be a separate video. So let's go ahead and get started. All right, here what we have is 0.1 liters of HF. So we'll draw that in our flask, 0.1 liters, and it is at a concentration of 0.5. So that's our HF, and then what we're going to do is we're going to add NaOH to it. And from our problem, we can see that we're going to add 0.05 liters at 0.2 molar of our NaOH. So this is the point we're at in the titration, where we've added some sodium hydroxide. And what we need to do if we want to find the pH is figure out how many moles of my acid are left. Or if I've added so much base that my acid's all gone, how many moles of my base I have. And the way we're going to do that is with this here BARF table. So my BARF table is all in moles, all moles. All moles. And we're going to think about how many moles we started with of each thing, how many moles we changed when we added some of our sodium hydroxide, and our final moles that we have. Before we can use our BARF table, though, we need to write our neutralization reaction. And that's just what happens when we react our acid with our base. So we were going to take HF, and we're going to react it with our base. Remember, there's just OH minus ions floating around down there, so we can write it as OH minus. And this reaction is going to basically take the proton from my fluorine, and it's going to transfer it over to my OH minus. So all we get out then is my F minus, because it's lost the proton, and H2O, which is a liquid. So that's my neutralization reaction. And in my BARF table, I'm going to track HF, OH minus, and F minus. I don't need to worry about water. It's not going to impact the pH. And then I'm going to write my beginning moles. So notice that I start out, before I add any of my sodium hydroxide, I have no OH and no F minus. So beginning moles basically means imagining all my HF together in the bottom. And if I want to calculate the moles, then I have to use my molarity equation. So it's really important for BARF tables to keep in mind that molarity is equal to moles over liters. And that means if I want to go to moles, I need to multiply it liters times molarity. So for HF, to get the beginning moles, I'm going to multiply liters, which is 0.1, times, let me give myself a little more space, 0.1 liters times 0.5 molarity. And what that is going to do is give me moles, and it turns out that's 0.05 moles. I have no hydroxide or fluorine to start with. And then what do I add? I add sodium hydroxide, and I add 0.05 liters times my 0.2 molar. And that's going to mean that I add 0.01 moles. Okay, my addition, I didn't add any HF or F minus, so those are both 0. Now I think about the reaction. What happens when HF and OH minus reacts? Well, OH minus and HF are both reactants. They're going to drop in concentration. Meanwhile, F minus and H2O are going to increase in concentration. So my OH minus can drop by 0.01 moles, and so can my HF. Meanwhile, my F minus will increase by that same amount. Why is that? Well, remember, if I have just one HF, right, and I react it with the sodium hydroxide, that goes away and I get one F minus, right? So I'm always going to increase the concentration of my F minus by the same amount that I decrease my HF and OH. What are my final moles? Well, I get 0.05 minus 0.01 is going to give me a 0.04. 0.01 minus 0.01 gives me 0. And here I'm going to get 0.01. All right, now I've used the BARF table and I've written the neutralization reaction. I have to ask myself, am I before or after the equivalence point? Well, I'm actually before the equivalence point because I still have my acid left. Notice that there's still acid here. And that means that I'm going to calculate my pH actually with the Henderson-Hasselbalch equation. That's what that HH stands for. The reason that is I have HF, which is a weak acid, and I have F minus, which is its conjugate base. So this turns out at this point in the titration to actually be a buffer. We have a weak acid and its conjugate base. That's what a buffer is. The nice thing about that is it's really easy to calculate the pH of a buffer with our Henderson-Hasselbalch equation. So we're actually glad that we end up with a buffer here. If my acid was all gone, let's say I'd added enough OH minus that it was all gone, well then I would actually calculate the pH just using how much strong base I had left around. We'll do another problem like that in a second. Alright, so this is the situation we're in. We have HF and F minus. Okay, so this is my Henderson-Hasselbalch equation down here. And it allows me to calculate the pH by doing pKa. P there stands for negative log. So I'm going to take the negative log of the Ka, and then I'm going to plug in concentration of my base over my acid. This guy's my base. That may not be obvious, but what should be obvious is that HF is my acid. So, if I want concentration, remember that I have to use my molarity equation, which is moles over liter. It's also really important to remember that I started out with 0.1 liters of my HF, and then I added 0.05 liters of my NaOH. And that means my new volume total is 0.15 liters. So, when I plug in my concentration of my base, for example, I'm going to put in 0.01 moles divided by 0.15 liters, and that's going to give me my molarity. So let's go ahead and calculate the pH. pH is equal to negative log of my Ka, that's what pKa means. That's my Ka, which I got from the problem up there, plus log, up top we'll put the concentration of my base, 0.01, divided by 0.15. And on the bottom, we'll put the concentration of my acid, which is 0.04. That's my moles of HF, divided by 0.15. When I plug all that in, what I'm going to get is a pH of my whole system of 2.86. That's after I've added 50 milliliters or 0.05 liters of my sodium hydroxide. Okay, now let's do one more calculation where I'm going to add even more sodium hydroxide. So this says, for example, that I have initially 0.1 liters of my HF. But now, instead of adding 50, I'm going to add 300 milliliters of my NaOH. This, as you may expect, is going to bring me beyond my equivalence point. So what does that look like? Well, my beginning moles of HF are still exactly the same. And my beginning moles of OH and F minus are 0. My OH now, I need to calculate the moles by doing liters times moles. And that's going to give me 0.06. Now, I didn't add any HF or F minus. Now I'm going to think about my reaction. Well, because I have 0.05 moles of HF, that's the most of my OH that could possibly react. I'm going to have OH left over. So I'm going to subtract 0.05 there and subtract 0.05 there. Because after that, my HF is gone and my OH will stop reacting. And then my F minus is going to increase by 0.05. That's going to leave me with 0 HF moles. It's going to leave me with 0.01 moles of OH minus, because 0.06 minus 0.05. It's going to leave me with 0.05 moles of F minus. Okay, so I've written the neutralization reaction. We just left it up from last time. I've used the BARF table. Now I have to decide, do I still have any acid? Well, no, I don't, right? My acid here is all gone. That means I'm going to calculate the pH with my strong base equations, and I know that I have a molarity, or a concentration of 0.01 OH. So let's go ahead and do that then to calculate the pH. I'm going to, once again, remember that I had initially 0.1 liters, and then I added 0.3 liters. And so what that's going to give me is a total of 0.4 liters. That's wrong up there. That should say 0.3 liters. So that's the new total volume. And then how do I calculate the pH? Well, I'm going to start with the pOH because that's what I have the information for. And this bracket, once again, means concentration. So I'm going to calculate the concentration to calculate the pOH. So I'm going to do negative log of my moles over my liters. Remember, that's how I calculate molarity. Molarity equals moles over liters. 0.01 divided by 0.4. And when I do that for my pOH, I'm going to get 1.602. Now, how do I calculate the pH from that? Well, I remember that my pH plus my pOH is equal to 14. And so that means that my pH is equal to 1.602, is equal to 14 minus 1.602. So pH in this case will be equal to 12.4. So that's the pH after I've added 300 milliliters of sodium hydroxide, gone beyond the equivalence point. All right, so that's how we calculate the pH during a weak acid strong base titration. You have to decide if you're before or after the equivalence point. In another video, we'll talk about what to do at the equivalence point. Thanks for watching this episode of